So the third session of the day is going to talk about high-performance network programming in Rust, an experience report that Angelo Corsaro from Zetascale we're going to talk about. So Angelo, in just a few words, he's the CEO and CTO at Zetascale Technology. At Zetascale, he's working with a world-class team to change the landscape of distributed computing, working hard to bring to every connected human and machine the unconstrained freedom to communicate, commute, and store anywhere at any scale efficiently and securely. Angelo is a world top expert in edge fog computing and a well-known researcher in the area of high performance and large-scale distributed systems. Angelo has over 100 publications in referred journals, conferences, workshops, magazines. He's also a co-author of over 10 international standards. Angelo, the mic is yours.
Thank you very much, Hassan, and hello everyone to today's session. So indeed, we're going to discuss about high-performance network programming in Rust. And I think before talking about performance, performance or high performance is sometimes kind of subjective to people. And everyone is convinced to have the need for high performance. But then when you start talking, realize that sometimes even the order of magnitude are different. So I think where we need to start is at least explaining or pointing out what we think, in our case, for our user, high performance means. So let's start from there, and then we'll derive everything else. So in our case, when we talk about high performance, we really think about we should be, with our communication stack, easily saturating 10 gigabit per second link, even for very small data. So we shouldn't even think about that, okay? And if we then switch to a little bit more powerful network, like perhaps a 100 gigabit network, then we should have, when running on top of TCP/IP, because as we will see, we can also avoid the use of TCP/IP, but let's say when running on top of an IP stack, so on top of TCP/IP or UDP/IP, then have performance that are as close as possible or as good as possible to what you would get with an iPerf, perhaps over a 100 gigabit network. And then in our case, when we mean high performance, we also mean that latency should be measured in the microseconds temporal scale. Once again, this is when running on top of a full-blown IP stack and across the network, okay? So this is for what concerns raw performance. Then there is another dimension of performance that we kind of, whenever, at least in our team, we think about performance, in a way we should perhaps say performance and scalability, because for us, raw performance without scalability is not really applicable then to the kind of use cases that we are applied with. And so when we think about scalability in the context of let's say, high-performance software, we think about the ability of scaling up to leverage machines that have many cores, and that takes proper architectural design, as you probably understand and will discuss quickly. It also means for us being able to scale down. So we want our software to perform well on a 80-core machine, but also perform well on a microcontroller. Okay, and that takes some design effort. That takes some careful thinking, and we will see how we go about it. But we also need our software to scale out at internet scales application. And again, to understand the challenge that we have, I will briefly introduce the kind of software, communication software that we write, and as a consequence, you will understand what are the kind of problems that we need to solve. And I think this will be a theme that I will be going through or recalling from time to time, because whenever you think about or you look at what other people are doing or the technology that they are using, or perhaps the library, as I will mention later on, you always need to try to understand if the problem they are trying to solve is the same problem that you are trying to solve, and if so, if they have the same performance constraints, because perhaps either the problem is slightly different, and so that is not necessarily applicable for you, or they don't have the same performance requirement. So you have to be very careful in making sure that both of those checkboxes are marked. Okay, that said, what do we do, or in which context do we use Rust? And then we will see why, and then we will move to the to the key element that we follow in order to write high performance Rust. And I will share with you some warning with respect to areas or surprise that we had that we really weren't expecting. And as we dealt with them, hopefully you want if you're also are interested in writing high performance Rust code. So some of you perhaps know, but some perhaps don't. One of the things that in our company we contribute is the Eclipse Zenoh project. So what is Zenoh? Zenoh is a communication protocol that unifies data in motion, data at rest, and computation, and is able to do that from the embedded microcontroller up to the data center. So what does unifying data in motion, data at rest, and computation means? In other terms, it means that we provide you in the same stack, and we will see real quickly, abstraction that allow you to do very efficient pub/sub, okay? But at the same time, in the same stack and with unified API, we allow you or give you the ability of performing geo-distributed queries. So if you think about data at rest, usually data at rest is stored in databases. Well, Zenoh, as we will see, provides you with plugin for, doesn't matter what kind of backend. A backend could be a traditional database, a file system, just about anything. But at the protocol level, it provides you with a way of distributing query to the relevant data stores and consolidating data back. The result of this capability is that all of a sudden you can store data in a decentralized manner, which is essential for edge computing. And at the same time, you have location transparency for data at rest. So when you're using a database without Zenoh, you need to know if the data is stored in that database or that database, in that data lake or that data lake. With Zenoh, if you just provide plugin to those data lakes or databases or data stores, file system, whatever, all of a sudden you use the Zenoh query routing to actually introduce location transparency. And the same primitive that we use to expose data sources, as we call them, data well, in the network, can also be used to abstract computation. This is why we say that we unify data in motion, data at rest, and computations. Besides that, although I won't necessarily cover it today, we provide on top of Zenoh a data flow programming framework for building, once again, cloud to microcontroller application and following this programming abstraction that is quite useful for distributed computing and especially data-intensive distributed computing. Now, going back to the networking aspect, Zenoh runs or can run starting from a data link. So if you're familiar with the OSI networking model, typically you have a physical, the data link, and the data link is essentially what allows you to transfer reliably or best effort, depending on the kind of data link, okay, data from point A to point B. As an example, Ethernet defines a physical and a data link layer. And then usually on top of Ethernet, you put an IP stack. But what this diagram says is that we can run on top of Ethernet without IP, or we can run on top of IP, or we can run on top of UDP, or perhaps on top of TCP/IP. As another example, because sometimes people don't think about it, if you think about a VPX bus, right? A VPX bus provides you with a reliable point to multi-point data link, okay? And so, for instance, in Zenoh, we can run as easily on top of an Ethernet, on top of a generic IP network, or perhaps on top of a ComExpress or VPX, okay? So that's kind of interesting to understand. And likewise, other example of data link could be low power networks, okay? Where perhaps you don't want to use the overhead, or you don't want to pay the cost of the overhead introduced by IP networks and to use straight Zenoh. So as we will see, the way in which Zenoh was designed, as we wanted, to be very low overhead, very high performance, and be able to run, as I said, on high-end as well as very constrained devices, and perform well on high-end and on constrained network, we really wanted our wire protocol to have very small overhead, because that helps with throughput on high performance network and helps saving bandwidth on a low power network. As such, the protocol is designed in such a way that We have very low wire overhead. It's just a few bytes, meaning around, depending on how you configure the protocol, between 4 and 6 bytes. And as we will see, although from an application perspective, you use resources to address data, those names never go on the network, or depending on how administer your network, might never go on the network, or only go on the network when you register new resources. Okay. So just to give you a glimpse, we can run obviously on your workstation, on your mini-core machine, but we can scale down on very small things, and you have some example. So you can have Zenoh running on ESP board, on Arduino, on Zephyr. We recently have it running on Mbed, you name it, and then obviously would run on your typical workstation as I just mentioned. And in terms of abstractions, you have a resource abstraction. So the resources are represented with a key and a value, as you see here. A set of resources can be identified with a key expression, and then you can further select these resources by using selector, in which you have identify a set of resources with a key expression, and then you can have predicate to identify just the resources in this set for which the given predicate is true, and then you can have even projection. So among those resources that you've selected for which the predicate is true, then you want to project just certain fields. So that's an example of the selector. In terms of the abstraction, you have publisher, which are a string of value for a key expression, subscriber, which allow you to express the interest to receive values for a key expression, and then this concept of a queryable that typically, I think we are the only technology that, or network protocol that does this network endpoint. A queryable is like a oracle or a well. It's a place where you go with a saw to put water. And so you understand that essentially our routing protocol routes data published from publisher to subscriber, and then when you issue a query, it does the other way around. It searches the queryable that can answer that query, in fact, the minimal set of querybles and the closest set of querybles that can answer that query. The queryable execute the query, return the data to our stack, and our stack consolidate the data back. Okay, so that just to give you the intuition. So how does writing or querying data from Zenoh look? And as this is a call in Rust, a talk in Rust, I'm giving you example in Rust, but obviously we support multiple programming languages. The stack is entirely written in Rust, but then we have bindings for C, C++, Python, Kotlin, and so on and so forth. So on the top of my slides, you see essentially that we are initializing the configuration by parsing the argument with parsarg. Okay, I'm not showing parsarg, that's not Zenoh specific. We are just then initializing or opening a Zenoh session. Several things happen when you open a Zenoh session, in between also some negotiation and so on and so forth. And then if you want to put some data, you simply call the put operation over the session for a key expression and a value, and that's it. Okay, that's all you have to do. Likewise, you see that this is an asynchronous Rust application. We provide synchronous as well as asynchronous API. In this talk, I will have special emphasis on asynchronous because it's there where you have to be very careful if you want to write high performance software, because there are some surprises or certain behavior that might caught you by surprise. What you see below on these slides is an example of issuing a query. So a query for us is like a get. Okay, I express my interest by using a selector, and I just said, look, get me the data that matches this selector. And that's our protocol that crawls the networks, and as you can see here, returns you streams of replies. Okay, notice that this code is beautiful and sequential, although there is nothing sequential in this code. The only reason why we can write sequential code and providing you this, very easy to reason, and again, a code without any inversion of control, is because of the asynchronous API. Is because of the support for streams that Rust provides as part of Async. And again, this makes code that is easy to use, that is easy to understand, and that for the end user, make sure that it's almost like operating on a container, although there are lots of things happening under the hood. Okay. So other things that I want to understand is that in Zenoh, we support essentially any topology you might imagine. And why is this important? Well, because if you think about the performance that we need to sustain, as we have, soft routers, so our routers are written in software, we support peer-to-peer communication, and a peer or a router can also operate as a broker for pure client, because some applications are not very powerful, so they cannot afford to do peer-to-peer communication, and so they need an intermediary to talk with other client or perhaps with other, peers and so on and so forth. So in this case, you notice that we have to ensure that we have performance that can be compatible with the performance of a backbone infrastructure like the routers, right? At the same time, and again, if you think about a routing network, you don't have so many incoming and outgoing links. You have those on the boundary of the network, but then you have pipes, and you have to make sure that you are able to blast as much data as possible through those pipes, okay? But if you think about the use case where a peer or a router is on the border of your system and is behaving like a broker, then all of a sudden you need to be able to efficiently scale and manage several different connections, potentially for client or peers. Okay, so those are challenges that we have to weight in our technology, and I'll explain how we do that. And Rust was actually quite good in dealing with that. So by design is extensible. As I mentioned, we have plugin for third-party technologies like MQTT, DDS. We're working on LPC UA integration as well. We have plugin for REST, plugin for databases, and so on and so forth. Now, let's look at performance, because then the rest of the discussion is explaining you how we got this far. So in terms of throughput, on a 100 gigabit network, we get very, very close to the peak performance delivered by iPerf. So you see that we are, around 50 gigabit per second already, essentially, with a payload of 60 kilobyte, okay? And we are 40 gigabit per second with a payload of 8 kilobyte. Notice also that we are saturating 10 gigabit link with a payload of 512 bytes, and we are saturating a 1 gigabit link with payload of 32 bytes. I mean, this is quite good as numbers, because any of you involved with communication software, saturating and being high throughput with small data is rather hard. And I mean, this is done by advanced scheduling in our communication stack, okay? So two things to retain here. On 100 gigabit network, we are very close to the limit provided by iPerf. And by the way, in this case, we are running on top of IP, because if we were sitting already on top of Ethernet, we could have better performance. And if we were to exploit in this specific network RDMA technologies, obviously we'll be very, very close to the 100 gigabit per second. But once again, we are running on top of IP in this scenario. And the deployment is peer-to-peer. So we have a publisher and a subscriber, and we are measuring lossless, reliable throughput. Okay, so there is reliability also involved. The latency across this network is a little bit over 30 microseconds. As you know, there is always a compromise between high throughput and latency. And with default settings, this is what you get out of Zenoh, okay? Then depending if it's more important latency versus throughput, there is some additional configuration that you can do on our networking stack. But off the shelf, this is the performance that you get that we believe are not bad at all, and way beyond what most of the application need. Okay, so if we want to put this into perspective, then let's, for instance, compare Zenoh with MQTT. So in this case, we were comparing it with a Mosquito broker. And in this case, just to do apple-to-apple comparison, we had publisher, a broker, and subscriber for MQTT, and same things for Zenoh. Okay, so in this case, in Zenoh, you will have a little bit lower throughput because there is an extra hop. And here you see the difference in terms of messages per second as the size of the payload grows from 8 bytes to 65 kilobyte. By the way, in the previous drawing or diagrams, you saw that we were streaming data up to 1 gigabyte. Obviously, we don't have limitation. We do fragmentation, as you might imagine. But that's just to prove that even if you're sending relatively big data payload that doesn't create problem to the stack. In this case, we are stopping to 65 kilobyte, but what you see here is that the performance delivered by Zenoh compared to MQTT, I mean, it's 4 times in terms of throughput higher. And if you look the number of messages per second for small data, I don't know many times it is better, right? So the point is, you can measure this two ways. You can say, wow, great raw performance, or if you are thinking about constrained devices, then you say, interesting, because all of a sudden you can say, if it's delivering this performance, that means that it's using less CPU to do the same amount of work, right? So all of a sudden it means that if you're running on a constrained device, then we leave more CPU for your application, okay? That's the other way, an interesting way of looking at this data. So either you need very high performance, which is good, right? Or you say, well, I don't need this performance, but I want to make sure that my communication stack takes as little as possible in terms of the CPU, right? For doing the work that he has to do, because I need the CPU for my own business logic. So that's another way of reading this data when comparing, for instance, with MQTT. And again, for those interested, we have comparison with our technology also. Okay, so in terms of seeing Zenoh in action, some of you perhaps have heard that it was used by the India Autonomous Challenge. I will go real quickly here. We have Zenoh used in autonomous trains and so on and so forth. So let's move now to Rust. Why Rust? And the key suggestion on how to write high-performance Rust. So first of all, let me open a small parenthesis on our journey on programming languages. So for what concerns me, 20 years ago, so it was almost 20 years ago, a little bit less than 20 years ago, I was doing lots of C++. And by the way, back in early 2000, I had even written a real-time Java runtime and compiler in C++ that eventually flew the first UAV, or flight control software for a UAV. So I know C++ very well, right? I like it as a programming language. But again, having a background on functional programming languages, I was always missing something in C++, right? There were certain things that I was missing that I always thought it was great. And again, there is another problem, that if you're looking for an high-performance programming language, great. High-level abstraction, great. I mean, one of the fantastic things of C++ are templates, so powerful, right? But then if you look at the number of issues that are created either because of concurrency or memory management, and the portion of those that are exploited for security, it's insane. I mean, there was a report recently from a security firm, and I believe another one from Microsoft, that stated that 70% today, 70% of the security issues are related to memory management problem. And so if you're using a non-memory safe programming language, I mean, you are exposing yourself to those problems, right? So after strong past in C++, well, mostly C++, then the first version of Zenoh was actually written in OCaml. So not sure how many of you know OCaml. OCaml is one of the ML derivatives. It's a great programming language, but delivers very good performance, very high level, memory safe. But there were a couple of problems with OCaml that at least we were facing. First of all, there was, although the OCaml garbage collector performs very well, there was still a garbage collector, and we were still not very happy about the level of jitter that we were having on some low latency use cases. The performance we were getting were very close to C, because the OCaml compiler is just terrific, but the garbage collector was just bothering a little bit. Then there was another problem with OCaml, which was the fact that back then, we didn't have support for multi-core. There was very good support for asynchronous programming that for us was very good. I mean, the asynchronous framework is very, very effective, but there was no multi-core support. The multi-core, was supposed to be coming next year, but every year was next year. And it has been merged into the main trunk only this year. And then the last point was a matter of community. So, there are some niche. Obviously, there is a niche of OCaml developers and a niche community here in France. There is another one around in Yale. There is another one in Cambridge. but it's not the most widely used programming language in the world. So we decided to switch. We knew we didn't want to get back to C or C++. We had evaluated Rust already in 2015, but didn't feel it was ready. And then again, in just about, I think it was 2019, 2020, we went back and did another evaluation. And in light of the addition and the improvement that were made with the 2018 edition of the language, we said, yeah, thumbs up. I mean, now we can really move to Rust. So let's go. And we did a complete rewrite of Zenoh in Rust. And in the rest of this presentation, I'll tell you our experience and how to get into performance. So first of all, we find that Rust is an extremely productive programming language. Sure, there is a learning curve. I think that the learning curve depends on how much you are familiar with other programming languages and how much you try to resist the rules of Rust, especially the rules on ownership, right? Versus you just decide to adopt those rules and you realize that Rust put constraint on you. And you have to carefully think of what you're trying to achieve and design in such a way that is friendly and compliant with the constraint that Rust put on you to ensure that your application can be memory safe and concurrency safe, okay? Once you do that, I mean, we are very, very, very extremely happy with the productivity and the level of, let's say, defect in our software, which is very low compared to C or C++. We had similar experience with OCaml, in which once it runs, it works, okay? Which is always very good property. So the other things that for us was key is asynchronous programming, right? If you want to be able to efficiently deal with networking code, so dealing with lots of connections, and in our case, we deal usually, especially in our routers, potentially with multiple networks. I mean, multiple physical network. Could be multiple Ethernet or routing between, an Ethernet and a Bluetooth and so on and so forth. So for us, the ability of doing asynchronous I/O is quintessential because it makes our code easier to write, easier to reason about, right? And not so easier to debug, but debugging concurrent code is always complicated. And we will see what are the complexities that are inherent to async. But asynchronous programming and networking code, or scalable networking code, are almost, from my perspective, a synonym, okay? And again, one of the key points is trying to avoid, and in fact, completely avoiding inversion of control. Inversion of control, just to name it differently, is the use of callback. Okay, if I use callback, all of a sudden, my logic is scattered in several different places of my code, and it's usually very hard to understand, especially for a third party, to understand what I'm doing. If I don't have inversion of control, like in the example that I showed you early on with our query, my code looks sequential. Okay, so it's easier for a programmer to reason about it. It's easier to understand the property and the invariance, right? And that leads to better maintenance, less bug, and less pain for us overall. So in summary, right, why do we love Rust? Because it's memory and concurrency safe. So again, that improves your safety and security. And concerning safety, there was recently an announcement from AUTOSAR, which is a standardization organization in the automotive industry, that they've started a track on investigating the use of Rust in automotive and for safety critical software. So I think that's another point that reinforces the safety aspect. The second point is it has high-level abstractions. So traits, the way in which generic works, algebraic data types. It's a pleasure to work with Rust. For me, it's like a system programming language that is able to pick some of the neat part of Haskell, but maybe you see some of the Haskell book behind my back, and some of the beauty of ML languages. Because in the end, if you look at it, Rust, it is an expression language. And expression languages are really coming from the ML family. But then if you look how trait work, they are like type classes, kind of like type classes in Haskell. And then you have algebra data types. I mean, it's beautiful, it's productive, and it helps you create nice abstraction, which is nice. And this is one of the reasons why we didn't even consider Go as a programming language, because the abstraction level provided by Go is very low. You have to do everything by yourself. I believe they are just about, or they have just added generics, but generics weren't even there, which is really no-go for us. You have zero-cost abstractions. So again, anything that is added in Rust is done in such a way that doesn't hinder high performance. So it doesn't let your code size grow, it doesn't let your overhead grow either. And as I mentioned before, built-in support for asynchronous programming. Again, that for me is an essential aspect for network programming. Okay, so how do you get high-performance code with Rust? And again, here the accent is mostly on network programming. So what are the usual recommendations? So I've been working on a distributed system for a long time, and people that have been working in distributed system, high-performance distributed system, high-performance network programming, know that there are a bunch of rules that you shouldn't break. It's like, your commandments, right? So if we start with concurrency, one of the error, for instance, if you think at the average Java programmer, well, sometimes I've seen C++ programmer also doing that. They don't understand the cost of threads, okay? And even worse, they don't understand the devastating impact of having too many threads, okay? And thus the importance of having support for asynchronous programming. Again, many people think that, wow, we have this great abstraction of threads, so I can spawn as many threads as I want and my system will work great. Well, that works great on toy application. As soon as you try to scale your system, as soon as you get under load, you will get your machine trashing, and you will lose progress. Your machine will be trashing because of context switch between threads, and it will be just a mess. So the rule of thumb that people that work in this domain know is that by default you should think as if I shouldn't be used more than one thread per core. And if you're using more, you need to understand why. Because once again, if you're using, and I've seen that in some system, some software developed, Java programming is an example, but not just by Java programmer, way too many threads. That seems to work up to when you don't hit a given load and you are trashing your system just because of having too many threads that are fighting and context switching all the time. And as soon as you have too many context switch, you are dead with performance, okay? So that's the first point. It's not so much Rust specific, but again, Rust gives you a nice way of controlling the number of threads, because if you use asynchronous programming, all of a sudden, you can fix the number of thread, OS thread, and then a future that are scheduled on this pool of threads. Okay, so that's great. And you can even be more smart I won't have the time to cover executor, but you could potentially have executor that take different groups of cores and then, organize this executor for different elements of your stack, okay? Second point is limit, or as much as possible, avoid locking. So what does it mean? Well, there is certain locking that cannot be avoided. And I think the question is really, can you get by using non-blocking or lock-free data structures in that case? Because when you can, it's a good way. But think very careful on how you architect your software, because architecture also has an impact on the amount of locking that then will be required. And locking will kill your performance, right? Now, there is something else to be kept in mind, because you will be hearing that locking is always bad. There are really 2 points on this. One is the amount of locking that you have, okay? Second, well, in fact, let's say 3 points. The amount of locking that you have, whether you are locking threads or lightweight threads. So in the case of asynchronous, that's if you're using asynchronous, a lock sometimes is as efficient as an atomic operation, okay, if you're lucky enough. And then it's the level of contention. So locking with low contention with Rust Async is as expensive as an atomic operation, okay? Which means it's very cheap. Locking between OS threads is not cheap at all, right? Because you are getting into the OS. So once again, I'm giving you some key point to recall, expanding verbally, but again, there is I think it's very good to move when you write high performance concurrent software to async, because even then, if you have to lose some locking, then if you design your software in such a way that those lock are in any case under low contention, your lock most of the case will be as expensive as an atomic operation, which is very cheap. The other point is limit context switches. Again, context switches can kill your performance, and especially context switch between OS threads. They will get your system trashing. So limit the number of OS threads, and then if you have context switch, think of context switch between green threads or again futures, because that's very cheap. Very cheap between quotes, because we will see there are some hidden traps there as well. Second point, memory. Okay, again, these are kind of generic, and then I will give you perhaps some twist for Rust. In your critical path, you should limit or ideally completely avoid dynamic memory allocation. Okay, so in Zenoh, essentially in the critical path, we practically avoid dynamic memory allocation, and if there is a dynamic memory allocation, it's the very end on user land, let's say, and it's mostly copy and write. So dynamic memory allocation, it's rather expensive. And again, here I mean heap memory allocation. Again, it's rather expensive when you're operating at our scale of time. If you don't care, I mean, if you are writing an application that operates on the milliseconds or seconds, fine. But then you have to be cautious of something else, which is memory fragmentation, potentially, right? So keep that in mind. The other point is that good performance need good cache behavior. And that's true for the instruction cache as well as the data cache. Not all data structure are the same with respect to caches, right? If you have data structures that are non-contiguous, and so they are using pointer, I mean, those are not very cache friendly, right? Because in a way, you cannot use spatial proximity, in order to leverage the prefetching that typically compiler and modern hardware does. Okay, so think very careful the data structure you use. Favor contiguous representation of data structure. For instance, just to give an example, in our routing graph are not implemented by using dynamic data structure, but they, as much as possible, they are represented in contiguous memory. Again, you can look at the code for more information. There are some nice libraries that also help you do that, but keep this in mind, because cache affinity is very important, and spatial locality is super essential if you want to have good performance. Last point, which is a general rule, is measure, don't guess, right? Systematically measure performance. There are lots of very good tools. Build performance tests that are relevant to the application. If a criterion isn't enough, and if you're working with networking software, that's highly likely that you need both. Look at the raw data and do proper statistics. Try to understand outlier. Look at the raw data, because sometimes there might be weird behavior, and then profile your code using perf, vtune, or some of the tools that are there. Okay. Now, avoid surprises. What do I mean with avoid surprises? So if you plan to rely on a library, then when you choose a library, make sure you evaluate it, especially if it's a core library. Never pick a library because everyone else uses it, okay? Because maybe they have different needs than you do. And I want to provide you a cardinal example of this. So let's look at the sync libraries. If you are into Rust, you know that everyone uses TOQ. We use Rust Async. Why? Because we measure. Okay, let me try to explain you what is the problem. So if you look at the various different asynchronous framework, and there are plenty of those, some of which are mainstream, other which are rather exotic, but the two main framework are Tokyo and Async STD. The vast majority of Rust programmers use Tokyo, But Tokyo, and we have raised this to the last programming language we are discussing with the Tokyo team, has some performance issue. So here you see the latency induced by Tokyo when compared to async STD or synchronous, let's say, socket programming in Rust. And you see that this is a logarithmic scale, that Tokyo kind of plateau at the level that, it's much higher than async STD. So there are, we are at 7-8 microseconds for async STD, and we are almost at 20 microsecond latency for Tokyo. I mean, that's way too much for us, okay? We cannot pay for that extra cost. And to make things worse, if you look at behavior under contention, so if we have multiple synchronous tasks running, then Tokyo completely starts misbehaving. So once again, my recommendation is, whenever you pick a library, understand if other people have a use case that is really like yours, right? Because Tokyo is used by lots of networking framework, but perhaps they don't have the same performance requirement like us. And there is nothing that can replace measuring it, okay? So this is for us a tricky situation because, as you know, the vast majority, usually there is a group effect. So some people or big companies use Tokyo, everyone uses Tokyo, although Async delivers better performance. We are engaging with the community, with the Tokyo team, with the Async team, and the language team to try to sort this out and make sure that, Tokyo perhaps improves their performance, or, we make sure that sufficient work is put into Async STD. The last point that I want to raise, and then we'll move to questions, is asynchronous programming is great, but it's hard to profile its performance, because when you start looking at the profile, the first time you get your eyes crossed and then you kind of get used to it. And the things that you have to be super careful is, do not consider or under-evaluate the impact of the stack size of the futures on your performance. So every future in Rust is a state machine. And each time you have, and the bigger is your future, the bigger is the state machine. And as you chain call, the state machine gets bigger and bigger. The impact of this is that each time you make a call, you have to copy this state machine. And if the state of your future is rather big, obviously you have an overhead that is linear in the size of the future. You can profile that with Rust. Make sure that you look at the size of your futures. Having big future or big stacks in future will kill your performance. So watch out for that, because we'd be beaten by that once. I think we were some of the first to be beaten, and then we learned the problem, but now we share it with you so you don't have to undergo the same problem. So in summary, and there we are just about in time, the path to performance is all about a disciplined step after step journey. You have to measure, you have to profile, you have to understand, and if you don't understand, you have to keep analyzing up to when you understand. Trust me, to figure out that some of the performance problems we were having were the size of the future, was not a snap of a finger, but only the discipline and a very analytic approach will get you there. So many of the tricks that apply to C and C++ continue to apply. So if you're using to high performance computing and high performance network programming, some of the idioms and the principle will continue to apply. There are some specials, and again, some of those specials are specific to async and futures. And again, I gave you some of the key one. There are some others. Real briefly, watch out async traits, because those induce dynamic memory allocations, and so on and so forth. So that concludes my talk. I hope that this was interesting and hopefully useful for you. And overall, we are super happy with Rust. It's a great language, great community, and looking forward to hear your feedback and question if there are.
Absolutely. Thank you so much, Angelo, for the great presentation. I think we had a couple of questions, but before we look into those questions, I think it's fair to share with the community that the Eclipse IoT working group, in partnership with Zetascale, are putting together an Eclipse Zenoh Summit on June 16.
Yeah.
So that few weeks from now. Stay tuned for the program details and the speaker profiles and details. We're looking forward to have an in-person event on June 16 in Central Suplec in France. So stay tuned for further details coming out sometime next week over our social media channels to communicate the program and the speakers and the rest of the details. So we all look forward for this event, June 16. So I'll move to the questions, and I've got a few questions here. Let me just go back to this session. All right. So I got the first question from Alexander. So throughout the slides, was any type of network encryption like TLS for HTTP used for the measurements and for the comparison between MQTT and Zenoh?
No, because so the point is, that would just add overhead that is not necessarily intrinsic to the performance of the stack, right? So, and that depends on eventually using accelerator. So there we were measuring really the stack on plain networking. And if you add encryption, obviously that will add, but then it's not, it's adding some overhead, but there you have the baseline, okay? We have the numbers for the additional cost added by the encryption layer. We can share that, and maybe we'll share those on a blog. By the way, usually what we do, and there is some additional material, so perhaps I will post a link. But on the Zenoh website, on the blog session, okay, we always keep blogs about various things. And so, for instance, you will find some additional detail on the evaluation that we did on Tokyo versus Async STD, and so on and so forth. So, we might share some of the data on our blog coming up.
Okay. Sounds great. And in all cases, I'll put the links right after this session on the chat box for everybody to take a look. So a follow-up question as well. Would it be possible to use Zenoh with an RTOS, like FreeRTOS or ThreadX, or Zenoh replaces RTOS by itself?
Okay, good question. So we have not ported to FreeRTOS yet, but yeah, definitely. Shouldn't be a big challenge. So what I suggest, the Zenoh community, and if you want to ask question, you can actually do it through our Discord server. I'll post a link, and feel free to ask that question on the Discord server. So here's the link. And concerning ThreadX, we are actually already running on OpenThreadX as part of the Brittle Mouth program. I don't know if any of you is familiar with that, but that's a standard for maritime drones. The drones that do deep ocean explorations. So that's a very complicated environment because vibration, humidity. So you have very embedded nodes with high quality hardware and low power network. In that context, we are already running on OpenThreadX.
Sounds great. So Alex is also asking if Zenoh conference will be in person. Oh, okay. So yeah, the Zenoh conference will be in person. We will be trying to record the conference, and then we'll be broadcasting the conference over the social media channels. We'll put the details next week as we approach the announcement of the program details.
Yeah, and so the idea was, right, Hassan, that depending on the time zone, because it will be in person. So when we are in person, for those that cannot travel, we'll also stream on our Discord channel. Okay,
yeah.
So we will let people to attend, let's say, virtually through Discord, and then still record, so that those that because of time zone or maybe another engagement cannot attend, you will still have the recorded session.
Perfect. Yeah, I guess all of this information will be flushed out next week, and all the links will be there for everybody to watch at a later point. Angelo, thank you so much. I really want to thank you for this great session. I think I think it was quite informative session. We will be taking a 10 minutes break before my colleague Frederick welcomes a panel discussion from academia from Stellenbosch University. So stay tuned for the next session. Thank you so much and have a lovely day.
Thank you. Take care. Bye-bye. Thank you, everyone. Bye.